So what we're going to look at with these optimization problems is often you're trying to find what is the best thing to have happen, or what's the, if you're looking at making money, businesses are interested in finding, well, when can I make the most money? When can I maximize my profit? When building something, they're going to look at, well, when can I make the maximum volume, or when do I get the maximum area? And we've done questions like this in the past in grade 11 when we had parabolas. And we had a bunch of different situations where we had a parabola and we were trying to find out when am I going to get the maximum area for my chickens in a chicken coop if I've got a certain amount of fencing. Or when can I get the maximum profit if I charge a certain amount for selling coffee, but each time I increase the price, less people are going to buy it. So how do I set my price to make the most money possible? Now those are some of the things that we did back in grade 11. We get a look at those again from a calculus viewpoint and see how we can do them even easier now than what we used to. Because what we used to do with parabolas is we had to complete the square to find the vertex. And it was always the vertex that was either a maximum or a minimum. Now we'll be able to do calculus and take the derivative, because we know that those maximum and minimums happen when our derivatives are 0 or when our tangent lines are horizontal. So this is our setup. We're going to solve these. We're going to set up our variables with our unknown quantities, and we're going to try to set up an equation. Sometimes that equation will be easy to set up, sometimes it'll be given to us, and sometimes it's going to be quite difficult to set up because we'll have multi-variables present. Because some equations have 3 unknowns in them, and then we're going to have to do some rearranging to make sure that we set up our variables and set up an equation in 2 variables, not 3 or 4, depending on the question. Once we get that derivative, we'll set it equal to 0, because that's where our line will be horizontal. And then we'll look at our answers to see if they're reasonable, right? Finding the maximum area of a box where the side length is -5, all of a sudden you have to say to yourself, hey, wait a minute. Something's not right here. So we have to always think about the context of the problem, what's reasonable and what's not. So here's a very basic question that comes from grade 11. We've got a ball thrown vertically upwards. Here is the equation. Based on the equation, we know that this is not on Earth because it doesn't have a proper gravity, but we won't worry about that because we're just trying to get an idea for the calculus. So the equation is given, and it's already in 2 variables. The variables are y and t. So we can find the derivative. And by finding the derivative, dy dt, we can set that equal to 0 and calculate when it's going to be at its maximum. So we get our time is 7.5 seconds. And getting that value, I think, is relatively quicker this way than if you had to complete the square. Now, completing the square doesn't take too long, but the derivative is a little bit faster. Now that we've got the time, we can find the y value at that time by just plugging that into our calculator. See what value I get here. $56.25. So we can write a statement. The ball reaches a maximum height of 56.25, and the units we're using, meters, at 7.5, and the units we're using, seconds. Here we're given the context of a question, but we're not given the equation. But again, it's one of the ones we had back in grade 11. There's a building on one side of the lot, so we imagine some sort of building here. Ooh, slanty building, pretty building, perfect. There's our building, and we want to enclose a rectangular parking lot with 60 meters of fence. Nice. Nothing like a parking lot you can't get into because there's fence on all the sides and a building on the other side. Perfect. Fred should think about this a little bit longer. Anyways, this is what we have. We've got 60 meters of fence for the whole thing, and we can change the shape of our rectangular parking lot. We could make it, for example, we could make these sides 10 meters and 10 meters, and then you would have 40 meters left. Seems reasonable. Or we could really wonder about Fred and say he made this 1 meter by 1 meter, and then he would still have 58 meters left. So not only is that a wonderful parking lot, not be just for bicycles, I guess. But if that's what he wants, then that could happen. But he is trying to be smart, and he's trying to get the maximum area. So what we find out in these optimization problems that we're trying to find a maximum of, the question will say what you want to find a maximum of, and that's what you want your equation to be. It's got to be an equation for area. And it's got to be an equation for area with two other variables. But right now, we don't know how long this side is, and we don't know how long this side is. We do know that this side over there is going to be the same as the other one. So right now our area formula is x times y, and we have three variables. So our job is to use the context of the question and say, is there a way that I can write either x or y in terms of the other variable so that my equation in the end only has two variables? Now, we did this back in grade 11. What do we know y is equal to? Well, when we did those examples and I did 10, 10, and 40, how did I figure out 40? I subtracted the two 10s from 60. And when I did 1 and 1, I made it 58 because I subtracted the two 1s from 60. So once we've done a couple of examples with numbers, we start to realize what we're doing is each time if I use x and x here, I have to subtract both of those x's from 60 to see what's left. And now I can write my area formula with two variables. And if I expand this, again, this is exactly what we did back in grade 11. In grade 11, though, now we would go and complete the square. Now that we're in calculus, we can find the derivative make it equal to 0, and solve for x. And again, it's much quicker than going and completing the square. Now, if we think that this x is equal to 15 and this x is equal to 15, that means that this side here will be equal to 30. And we can write a statement here. Maximum area will be 15 meters by 30 meters, which is 450 meters squared. So for him, if he wanted to build a rectangular parking lot, that would be his best shape to build, using the fencing that he has. He could probably build it bigger if he left a spot open for cars to get in. But we won't worry about that right now. So what I'd like you to do on this one is, can you set up your equation for this? Again, we read through the whole question. We see that we want to find a maximum volume. So there has to be enough information in here to write an equation for volume with only two variables, volume equals. So here is a diagram that can help you visualize. Imagine your sheet of cardboard, and then you would have to cut out squares in the corners, and they want to be equal sides, so they'll all be x's. And then you can imagine folding along here, and here, and here, and here. And you'd create a box that would be open at the top. Well, volume is length times width times height, but now we have to write all of those in terms of x. Can you see that the height will be x? And then from both, on all these red lines, for both the length and the width, you take your value you started with, and you'll be subtracting 2 x's from all of those. If we expand that, you'll get 70x minus 34x squared plus 4x cubed. So now that we've got our equation, we can take the derivative. And the derivative gives us a large parabola that does not look easy whatsoever to try to factor. And so if you had to go to a calculator anyway for this, what I've done now is I've said, well, I could take my equation of my derivative and I could plug that into my calculator. It's a parabola. And so when I plug that parabola in, I'm going to find some x-intercepts. So here's a picture of the parabola. If you want to create this yourself, there's the window, because on your first window you wouldn't have seen the minimum. So if you just have your minimum go down to minus 30, you'll be able to see the vertex of that parabola. And we find 1, 0 happens at 1.35. Now if we look at the graph of our volume, and here's a picture of our original graph on our volume, and we look how it goes up and down, you seem to have a maximum volume here, then a minimum volume down there in the negatives, which should start to make you think something's wrong. But then the volume keeps on going up forever after that. So we have to say, well, why is this point our actual maximum and not something way over here? And here is where the context of the problem comes into play. If we look back at our diagram here, and we ask ourselves, what are possible values for x? In other words, what is the domain that we can actually look at? Well, I guess let's say we're building a box. We'll say it's waterproof because you've got a collection of water molecules that you just love, and you want to store them in a box. And so technically, I guess you could not cut anything out of the corners, and you just have your sheet of, was it cardboard? Yeah, so it's waterproof cardboard, perfect. So you've got your sheet of cardboard, and you haven't cut anything out, so you could pour water on top of it and it would just roll off. It would have no volume whatsoever. So I guess the smallest x could be 0, even though that would give us a volume of 0. But at least we could plug that in and we could imagine what that's going to do. That's not going to actually do anything to our piece of cardboard. It's just going to keep it flat. What's the largest square you could cut out? What's the largest value of x? Could I make x 50? Does that make sense? Could you cut a square of 50 centimeters out of the corner of that box? No. That would be not reasonable because the box is only 7 by 10. At what point can we not cut a square of size x out? 3.5. Now 3.5 is half of 7, so if you cut 3.5 out, again, you'll have something that'll have a volume of 0. In fact, you can see it from the formula here that in that set of brackets, if x is 3.5, that set of brackets will be 0. And again, you'll get a volume of 0. So when we look back at our graph here, here we have x equals 0. And here we have x equals 3.5. And in fact, the only domain that makes sense is this section of our graph. Because after that, we're not actually getting volumes that make sense. So in the context of our problem, that's our only domain. So now it makes sense that we only found this 0. If you went to your calculator and found this other 0, which looks like it happens 2, 3, just after 4, well, since the context of our problem doesn't make sense after 3.5, that x-intercept doesn't make sense. And since we're dealing with values that we'd have to use our calculator anyways, we may as well use the graphing calculator to see these values, to see where they're equal to 0, and then once we've calculated that, to get that value. Now I want to show you a couple of graphing calculator things just quickly that can help you. We're going to type this equation, if you haven't already. Type the derivative equation in as well as the original equation. So I'm going to type the original equation in y1, 70x minus 34x squared plus 4x cubed. And then the derivative in equation 2. I'm going to just set my window here to negative 30, and you know that you can go over to the equal sign and push enter to turn a graph on and off. So if you go over to the equal sign and push enter, it unhighlights that equal sign. So right now if I push graph, I'm only graphing the parabola that we had before. My window, I must not have pushed enter on my y minimum. So that matches up with the graph that we saw on our screen before. Now if I go to calculate, second calculate, and I want to find the 0, 2, and I want to find that 0 between 1 and 2, you know you can do left and right by moving your arrow keys over and over again. But if you can see where it is, you can get your left bound quicker by just typing in a number. So I'm just going to type in 1. It'll automatically put it at 1. And the newer calculators are nice because they'll even show you a line where it's at. And my right bound, I can see that 2 is going to be nice. So it's in between 1 and 2. And here we get our 1.35. Now, whenever you solve something, it temporarily puts it at x. It doesn't store it at x. It temporarily puts it at x. But it's going to be helpful for us so we don't have to remember all those decimal places, that we actually store it as x. So now I've got it stored as x, and the reason I wanted to do that is because I go back to my y values, and now I'm going to turn on my first graph and turn off my second graph and look at the graph. Of course, now my window isn't set up very nice because it goes off the top. We'll set up our window exactly the same as we had here before, which gives our y max at 50. So, a couple of things. If I want to find the y value when x is 1.35, well, I can calculate a value, number 1, and since I stored x as x, we'll see if this works. No, it didn't. Shoot. Well, that was worth a try. I wonder if I stored it as a different value. X is 10 now. Wonder why it overdid that. 1.35, we're going to store it as a, not as logic. We're going to store it alpha a. Enter. Okay, we're going to try that one more time. Calculate the value when it's equal to a. Yes, it worked. Nice. I don't know why I didn't want to store for x this time, but it did store for a. Maybe it was confused when I said x is equal to x. Now, of course, we wouldn't have needed to do that because we could have calculated that maximum by just going to number 4, maximum. We can see that our x value is between 0 and 3.5 because we know those ones are the only ones that are reasonable. Number 4, maximum. Left bound 0. Right bound 4.5. 3.5. Oh well, that'll be good enough. And we could have found that same maximum that way. So we have a couple of options. Since we know we're finding the maximum, it's just nice to know that when you get a value from your calculator, that you can store it and collect it and keep all those sig figs. Okay. So there we have our maximum volume, obviously a calculator question. So again, here's another one. This one's not as difficult. I'll get you guys to try this one on your own. The numbers are nicer than the volume question. See if you can set up the equation and then find the maximum area of the triangle. So length BC in terms of x, well, you know that both of them have to add up to 6. So if you get the y by itself, which is length BC, you'll get 6 minus x. Now, our area of a triangle formula is 1/2 base times height. So if we plug that in terms of only x, and we multiply it out, we get an area of 1/2, negative 1/2 x squared plus 3x. And if we take the derivative of that, we just get negative x plus 3. Solving for x tells us that x needs to be 3 centimeters. So now if we want to calculate our maximum area, we know that our other side also has to be 3. And we get a maximum area of 4.5 centimeters squared. So again, we can set up our two numbers, our x and y, and it's all right to start off with the different variables. We want to find a minimum sum, so we're going to want to set up an equation that's sum equals. So with our two equations, we know that both of them, x times y is equal to 48. So you can rearrange that to get y in terms of x by just dividing by x, and you'll get y is 48 over x. That way, when we set up our equation for our minimum sum, here's our first number. If we take 48 and multiply it by 3, we get 144 over x, as our second number equals s. Doing our derivative here, we're going to get 1 minus 144 over x squared. What I did here with 144 over x is I thought of it as 144x to the minus 1. That way you bring the minus 1 out in front, make x to the minus 2, and you'll get 144 over x squared. Now when solving this equal to 0, if we get a common denominator and make this into a fraction is equal to 0 when the numerator is equal to 0. So all we need to do is solve when x squared minus 144 is equal to 0. That gives us plus or minus 12, but we need a positive number, so 12 is the only one that makes sense, and then our other value has to be 48 over 12, which is 4. So the two numbers have to be 12 and 4 in order to get that minimum sum. All right. Find the dimensions of an open box with a square base having a total surface area of 192 centimeters squared if its volume is a maximum. So we know that our goal is to set up an equation volume equals, and we need to do that in only one variable. If we draw a picture of our box, it looks like this. We know it has a square base, so this side and this side have to be the same. But we don't know its height, so we'll temporarily label it as y. So our volume right now is x times y. And we have 3 different variables in that formula. So we need to somehow figure out how we can either change the x or the y. Probably most likely we'll change the y because there's only one of them. How do we write that in terms of x? The other piece of information that we're given is our surface area is 192 centimeters squared. So maybe there's a way that we can use our surface area to figure out what either x or y is. Now, how do you calculate surface area of an open box? Area of the sides and the area of the bottom, right? So if we take the area of the bottom, we get x squared. Does it make sense that one of these sides is going to be xy, and you have 1, 2, 3, 4 of them all the way around the box? And this problem probably should have been even clearer and said an outer surface area, and we're not going to count the surface area inside the box. So we know that x squared plus 4xy has to equal 192. Could we solve for y? Well, yes. If we moved the x squared over and then divided by 4x, we get y in terms of x. It doesn't look pretty, but that doesn't matter right now. So now we can set up our volume formula. Well, we had x times x, which is x squared, and it's going to get multiplied by 192 minus x squared all over 4x. One of these x's will simplify. 192 divided by 4 is 48. Yes? So we are going to get 48x. Oh, I can't. Well, here, I'll keep it over 4 for now. We're going to get 192x minus x cubed all over 4, which is the same thing as 48x minus 1/4 x cubed. So now that we've got our volume formula in terms of one variable, well, now we can take the derivative. And the derivative here is going to be 48 minus 3/4 x squared. Setting that equal to 0. And solving. Divide by 3, multiply by 4, you get 64 equals x squared. So x equals plus or minus 8. But based on our idea, the only one that makes sense would be that x is equal to 8. So I got the 64 by multiplying by 4 and dividing by 3. Now what are we asked to find? Find the dimensions of an open box with a square base having a total surface area of 192 centimeters if the volume is a maximum. Well, now we've solved for x. We need to solve for y. We had our equation for y. Y was equal to 192 minus x squared over 4x. So if we plug in 8, four times 8 is 32. If we plug in 8 here, what do we get? 192 minus 64. And we get y value is 4. So we can write a final statement for our question. Someone see at the top of the question what our units are? Is it centimeters? So we have a height of 4 centimeters and an 8 centimeter by 8 centimeter base. So recapping in this question, we drew our diagram out. We noticed that our volume formula had two variables on the right-hand side, x and y. So we had to come up with some way of changing one of those variables in terms of x as well, or the x in terms of y, so that we could solve. The question gives us enough information here, the 192 centimeters squared for the surface area, so that we can rearrange and get y in terms of x. Once we've done that, we plug that back into our volume formula, and then we do the same thing, find our derivative, set it equal to 0, look at our answers within the context to see what's reasonable, and then find our final answer. So this next question, I'll get you to try it. It is equations given to you already, so that part is done, and that's easier. So they figure out the cost of storing units and delivering it is that equation. You need to find what order size will minimize that cost. So we can take the derivative, set that derivative equal to 0. Solving, you get plus or minus 100. Only 100 makes sense. If we think about drawing our first derivative test, we see that our functions would be decreasing before that and increasing afterwards. So in order to minimize the cost, x would have to be 100 units. It's important to do a little check here that it is actually a minimum, because if you did it and we only could find the maximum cost, then your company wouldn't be very happy with you. Done the calculus and you send everybody out and it's costing them the most possible every single time. Could be a problem. All right, let's see how you did in part A. So if we know that the volume is 54 pi, and our volume formula for a cylinder, pi r squared times the height. If we rearrange this, we're going to get our height to be 54 over r squared. The reason that's going to be important, because if we go to our surface area formula, our surface area formula is 2 pi r squared plus 2 pi r h, but what we're supposed to show that doesn't have any h's in it. So we needed to solve for h to get h by itself, so we could plug that in for h, multiply things through, and we do get our surface area to be 2 pi r squared plus 108 pi over r. The reason that's important is because in part B, we're asked to find the surface area that makes it a minimum. And so we can take the derivative and solve for this. And this becomes an important question. If we think of a real-life application of this, we see cylinders all over the place. Cylinders made out of aluminum, cylinders made out of tin. So companies are looking, well, if I'm going to make a cylinder for a can of Coke or a can of Pepsi, what size should I make so that I can use the least amount of aluminum possible so it doesn't cost me as much to make? And so we get different sizes, and we could look at, is the design that they currently have, based on mathematics, is that the best design that they could make? Or should they be fatter? Should we have fatter cans? Nice big ones that are really not very tall that you drink like this. So this one mathematically was set up in such a way so that we would get a nice r value. So setting it equal to 0 and solving for r. Now when you have an r squared on the bottom, what I did at this time is I multiplied everything through by r squared to get rid of that fraction. That gives us an r cubed. We get that r cubed by itself. In cube root, we get r is equal to 3. Then plugging that r value into our equation for h that we solved for before, we get 54 over 9 and get a height of 6 centimeters. And there's some questions at the bottom there that can practice some more optimization problems.